So to analyze this, I'm going to look at a contour plot of our f of xy function. So looking at this f of xy function, I'm going to set my z value equal to 0. So if my z value is equal to 0, I'm going to get y squared minus x plus 10. And if I solve this for x, it means that x is equal to y squared plus 10. And so drawing this on a contour plot, so this is the bird's eye view, of the y-x plane, xy plane. I just traced out the level curve where z is equal to 0. And the level curve where z is equal to 0 gives me a parabola where my x and y coordinates are in the opposite direction of what we normally see them. And I have, when y is 0, my x-intercept is out here at 10. So we just found that this looks like a parabola somewhere out here. And this is the level curve where z was equal to 0. Let's try a level curve where z is a more negative value. I'm going to do another level curve where z was equal to negative 10, for example. That's going to be negative 10 is equal to y squared minus x plus 10. I can subtract 10 from each side, and I get x equals y squared. So I chose this z value just because I know that it's going to land on this graph. And we see that we get another parabola, but this time it's been shifted backwards so that it hits right at the origin. And in general, if I were to draw all of my level curves, plugging in different z values, I would see that we would have the same parabolic behavior. You would get a bunch of parabolas all sort of going backwards this way. Maybe I'll draw another one. Right? And these values get smaller and smaller and smaller as I go in this direction, more negative. Oh, wait. This is my z value when z is equal to positive 10 for me to subtract 10 from both sides. I'm sorry. I should label this differently. So this was my z value where z equals 0, was way out here. Whereas this is my z value where z equals 10. And actually my curves get bigger and bigger as I go along. That was my error. This is the level curve where z equals 10, which is at higher elevation than back here where z was equal to 0. That's important for a maximization problem, that you want to make sure that your maximization is in the right direction. So let's go ahead. On top of this, we don't want to know the maxes and mins of this function f by itself. We want to know how they line up along our road, or constraint function. So in this case, our constraint function is a circle of radius 4. I'm not going to draw a super accurate picture, but I'm going to give some sort of an idea, right? So this is my circle of radius 4, and we have a couple of special places on this. We found that when our x-coordinate was negative 2, that's the place that was highest on the graph. And notice that that's going to be the place, it turns out, that's exactly parallel to this level curve right here. And this is the level curve z equals, oh, we erased how high it was, 57 fourths. And that's, I'll write this in red. So this is the level curve, and it's because these are symmetric functions, it's the highest place both down here and up here. That's a special level curve. And then at these points where x equals 2 and x equals negative 2, those are other special special level curves. Those are also level curves that are exactly parallel to my constraint function. It just turns out that only one of them is really that helpful. This is the one that's the lowest level curve that's exactly parallel to my road, whereas this one is a level curve that's parallel to the road, but it's just sort of some in-between point, and it's something that's not that interesting for us. And that's what we get when our x value was at negative 2 and our y value was at 0. So graphically, this mountain function gave us this set of level curves that start small and get bigger and bigger as they go this way, and the ones that are exactly tangent hit at that point of tangency right here. And that's exactly what our Lagrange multiplier method is telling us. So that was method 1 for solving maximization problems with constraints. We used Lagrange multipliers in order to be able to solve this problem. let's look at this problem, the same problem, a second time, only this time we're going to solve it directly by plugging in our constraint function into our function to maximize it. What do I mean by that? I said that pretty awkwardly. Really what I'm saying is I'm going to solve for one of these variables and plug it into my constraint function, because then I'll just have a function of one variable that I can easily find the max and the min of. I'm taking the composition, essentially, of this function with this function, and then finding the derivative of that. So to do this, there's a trick way that you think, this will be so easy. I have a y squared here, and I have a y squared here. So my first try, so this is my method 2, and I'm going to call it substitution, as opposed to using the Lagrange multiplier method. And I'm going to substitute, using this constraint, I'm going to solve and say that, well, this means that y squared is equal to 4 minus x squared. I'm going to take this, plug it into my f function, and I get f of x, y. Maybe I shouldn't say x, y anymore, because my y squared is going to become 4 minus x squared, and then I have minus x plus 10. So maybe I'll relabel this function. I'll call it like f1, because it's just a function of x now. And how do I find the maximization and the minimization of this function? I know I have to live on this curve, and so I just take the derivative of this function. The derivative of my f1 function is going to be given by, the derivative of 4 is just 0. I get negative 2x minus 1. I'm going to take my derivative, I'm just going to set it equal to 0. And when I do that, I see that I can, well, add my 1 to this side and divide by negative 2, and I get that x equals negative 1/2. I can plug my x equals negative 1/2 back into my constraint function. I just need to solve, right, because I use this relationship, and I see that that means that y is equal to plus or minus square root 15 over 2. Uh-oh. Danger. I did this substitution, and I only got out these 2 points, my max points, right? I got out the point where x is equal to negative 1/2 and y equals plus or minus square root 15 over 2. I didn't get out these other points. Why didn't I get out these points? Well, lamely, it's because of my choice of substitution. That squaring a function, it's no longer a one-to-one function, and some of our results are going to be lost. So I showed this intentionally because this is a case where some of our solutions are lost when you're not subbing in y, you're actually subbing in y squared. So this method is partially works, but I want to make sure that I solve for the exact variable. So I'm going to do it again, only this time I'm going to use my constraint function and I'm going to solve for x. Because if I solve for x in this case, I see that x squared is equal to 4 minus y squared, and so that means that x is equal to plus or minus square root of 4 minus y squared. I'm going to use this value to plug into this function, even though it's much, much more messy. I'll call this my f2 function. It's just going to be a function of y, and it's going to be equal to y squared minus the square root of 4 minus y squared plus 10. That's one set of equations, because that's accounting for when x was equal to the positive square root. And I'm also going to have an f3 of y function, and this is going to be y squared plus the square root of 4 minus y squared plus 10. And these are our new functions. I've taken the composition of the g with the f function, and we know what we want to do. We want to maximize this function. So how do I find the max points and the min points of this function? I'm going to take the derivative and set it equal to 0. So the derivative of my f2 function with respect to y is going to be 2y minus, I'm thinking of this, maybe I'll even rewrite it for visual sake. Square root is the same thing as raised to the 1/2 power, because now I can use my polynomial rule. The derivative of the outside becomes all this to the negative 1/2 times the derivative of the inside, which is negative 2y. The plus 10 just goes away. I'm going to rewrite this to make it a little bit more simple, because this chunk goes in the denominator. My negative 1/2 multiplied by the negative 2 go away. They cancel each other. Really, they're multiplicative reciprocals, and so they end up being equal to 1. That's the language that I should use. And it means that my derivative function is equal to something that looks like this. When is this derivative function going to be equal to 0? This is something that's sort of a crazy thought, right? I'm going to go ahead and factor out a y from each of the terms, because then I see that when I factor out my y, I can get 2 plus 1 over this crazy stuff. And I see that one of my solutions is when y equals 0, which corresponds exactly to these min values. When y equals 0, I get my plus or minus 2x just like I would like. So maybe we'll worry about this function in a second. I'll continue on here. So this just gave me the solution y equals 0, and that gives me the solution where x equals plus or minus 2. And I'll box that. But that's not the only solution. This is equal to 0 also when this chunk is equal to 0. And so that's going to be equal to 0. I'm going to do a little bit of subtraction and multiplication. That's going to be equal to 0 when negative 2 times the square root of 4 minus y squared is equal to 1. I move this over here, and I square it, and I get 4 minus y squared would be equal to negative 1/2. And solving for y, this will give me y being equal to plus or minus square root 15 over 2. Plugging in square root 15 over 2 back into our original equation, we get our x coordinates that we wanted, and that means that our x value in that case would be equal to negative 1/2. Technically, I would have to go through and solve all of those steps for this function as well. You'll find out that all of these steps will give us the same points that we saw before. So this is our direct substitution method, which is different than our Lagrange multiplier method. You can make a decision. Depending upon the problem, you might find that one is easier than another. All of them are going to use a lot of algebra.